So we talked about adding vectors together, subtracting vectors. We also talked about scalar multiplication, where you take a number and you multiply it by a vector. What about multiplying vectors together? Well, there's actually few ways to multiply vectors together. And one of the ways you could take two vectors and multiply them to get a number is called the dot product. Okay? Sometimes the dot product is called the scalar product because you take two vectors, say u and v, and you end up getting a number. What number is that? The number that is obtained by multiplying the magnitude of u times the magnitude of v times cosine theta, where theta is the angle between the two vectors u and v. Theta is also between 0 and pi. So if you wanted an angle between two vectors that's greater than pi, well, you could always find one that's less than pi. It just means that you decided to take the larger angle rather than the smaller one. So you always find the smallest angle between two vectors to get that cosine theta. Moreover, we call u and v orthogonal. So u is orthogonal to v and v is orthogonal to u. This I double f is if and only if u dot v is equal to 0. Okay? When the dot product is equal to 0, then these two vectors are said to be orthogonal. Now, try to think about why. So if u and v are not 0, okay, let's look at non-zero vectors, then how can you get this term to be equal to 0? Well, that means that cosine theta would have to be 0, which means that theta has to be pi over 2. And pi over 2 is 90 degrees. So orthogonal is another way of saying that u and v are perpendicular to each other. Now, if any of these vectors u and v were 0, then the dot product between them is just 0. Of course, that would be a little bit of a problem with that theta because you don't have an angle between the 0 vector and another vector, but so we just define it as 0 if u or v was the 0 vector. And again, this is sometimes called the scalar product because you get a number once you multiply these two vectors out. And you could also see that u dot u is equal to the magnitude of u squared. Now think about why that is. If you have two vectors that that are equal, so u is equal to u, what's the angle between them? Well, the angle between them should be 0. They're in the same direction. So cosine of 0 is 1, and then you would get u times, instead of v, you would have a u, so u, the magnitude of u squared. Just two remarks there. So let's try to interpret the dot product. Here we have two vectors. In purple, you have the vector u, and in green, you have the vector v. Well, if I took some light and I just shined it perpendicular to v, okay? So that is just shining straight down perpendicular to v. Well, this vector u is going to leave a shadow on v. That shadow we could find. So if these light rays are perpendicular to v, they're going to make 90-degree angle with a line that's normal or perpendicular to v. So then this length here, the length of that the shadow of u would leave on v, would be u times cosine theta. So what's the dot product in a sort of geometric way of thinking? It's the length that the shadow of u would leave onto v times the length of v. Now, you might say, well, why did you choose u? What if we chose the shadow that v would leave onto u? So if we instead had light that was shining down towards u and perpendicular to u, well then the length that the shadow of V would leave from light rays pointing down this way is going to be V times cosine theta. So if we take the length of the shadow that V would leave onto U and multiply it by the length of U, well, we'd also get this product, right? So you could either take V cosine theta and multiply it by U to get the dot product, or you could take U cosine theta and multiply it by V. So you could take U cosine theta and multiply it by V to get the dot product. Both of them work, and that's just another way of saying that the dot product is commutative. U dot V is equal to V dot U. So why use this thing, the dot product? Why is it useful? Well, suppose you have this box over here, right? And you want to move the box to this dotted box right here. So you're going to take the front of this box and displace it with a displacement vector d. So move it from here to here. And you're going to do so while there's this force F pointing in this direction. So here's a force. Well, you want to find the work. Work, not to get into physics, but this is something we should know in Calc 3. Work is equal to the force times the displacement. Okay? And it's basically the change in kinetic energy. Okay? Kinetic energy is, you could think about it as the kind of the energy due to the motion. So the work, change of kinetic energy, is equal to the force times the displacement. But what if the force is not in the direction of displacement? When the force is in the direction of the displacement, you just take the magnitude of the force and multiply it by the magnitude of the displacement. But a force that isn't aligned with the displacement should not contribute to the to any sort of work being done. It shouldn't contribute to a change in kinetic energy. I mean, imagine if while this thing was sliding, this box was sliding, you push down with a force towards the ground, and say there's enough, there's no friction, so it could slide down there without any friction. Well, why should a force where you're pushing down, or for that matter pushing up, but it's not moving in the direction of force, why should that contribute to a change in kinetic energy? And it doesn't. Okay, so we need a way to quantify how aligned one vector is, the vector of force, is with the displacement. Okay, and how we could do that is with the dot product. So thanks to the dot product, we could quantify how much along the force vector is to the displacement. So when we have a constant force, so if someone is pulling at a constant angle and with a constant magnitude for the force, then we could just get the work by taking the force vector and dotting it with the displacement. And again, how do you dot it? Well, you just take the magnitude of each of these vectors, multiply it together, and then multiply by the cosine of the angle between them. And here you notice, if force and displacement were parallel, if they were aligned, if they were in the same direction, then theta here would be 0, since they're in the same direction. And you would get just force times displacement times cosine of 0. Cosine of 0 is just 1. Okay? But if they're not, then that cosine theta helps us quantify how much along each vector is to the other. So let's start using the dot product. Compute the work done on a box displaced horizontally 2 meters. So a box moves 2 meters horizontally to, let's just say to the right, by a constant force of 3 newtons applied with an angle of 30 degrees from the vertical towards the displacement. Okay, so you have that last part's just telling you that you have 30 degrees from the vertical. Okay, so let's then find the amount of work. Well, the amount of work is the dot product between the force and the displacement. The displacement is, if we wrote it as a vector, the displacement would just be 2 meters in the x direction. Okay, but we're not writing it as a vector. We'll deal with how to deal with components in a second. But it's 2 meters this way. Now, this question was worded to trip you up. You don't just see an angle in the problem and just decide to throw it in there for cosine theta. We said that angle is the angle between the displacement and the force, right? So it's the angle between two vectors. And if that's 30 degrees, then that other angle is 60 degrees, or pi over 3. And we could just then use the dot product formula, which tells us that the dot product between the force and displacement is the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. The force has a magnitude of 3 newtons. The displacement has a magnitude of 2 meters. And the angle between them is pi over 3. So cosine of pi over 3 is 1/2. These two multiplied together is 6. And you get a total of 3 joules. Okay? So this would increase the kinetic energy by 3 joules. Now, how would you, what's a possible strategy to increase the kinetic energy even more by applying the same force? Well, what could you do, right? If you're still going to displace this by 2 meters and the maximum you could push that box is 3 newtons, what kind of strategy should you employ to get more kinetic energy into this, into the box's motion? Well, why don't you just decrease that angle? In fact, the more you decrease it towards 0, the better. Because cosine of 0 is just 1, and you could give a maximum of 6 joules to the kinetic energy. Okay? So that's why you would want to decrease the angle between them if you're doing work. You want to put all of your energy towards pushing that box's, in the direction of its motion. You could even be working in the opposite direction. Like suppose this box is sliding down towards this dotted area. Suppose it's sliding down towards that area. And suppose you apply a force, but backwards. Okay? So you could, maybe this is the frictional force, or maybe you were trying to push it back as it was sliding forward. Well, then what's the angle going to be if it's straight back? You're going to have an angle of 180 degrees between those two. And cosine of 180, or cosine of pi, is -1. So you would actually get -6 if you were just pulling straight back as it was moving forward. All right, so we defined the dot product by taking two vectors, right? You take vector 1, you take its magnitude, vector 2, take its magnitude, then you multiply by cosine theta, which gives you the sort of measure of how much they overlap. But what if you weren't given the vectors in terms of magnitude and a sort of direction? What if you were given instead the vector in components? How would the dot product then look? Well, suppose you have these two vectors, and here we're giving them in R3. The dot product between them is equal to U1 times V1. So you would just take these two first numbers, multiply them together. Add U2 times V2. Add U3 times V3 to that. And this is a theorem, okay? So we can prove this from having a definition that we begin with like that, okay? So if you define the dot product this way, you can prove that in fact it's given by this formula here when you have components. And the sort of sketch of proof of that, so not the official one, but a sketch of it, is you can draw the vector u this way, you could draw the vector v this way, and notice that u minus v, this vector here, closes that triangle. The rest is just using the law of cosines and noticing that this guy here is the dot product. So you could then solve for this guy here and plug in what you would have for u and v into these. So u squared, for example, would be equal to u1 squared plus u2 squared plus u3 squared. So you could then prove that indeed you would get this formula. So that's a nice formula, because if we're given two vectors, okay, u and w there, we could actually find the angle between them, right? I mean, here is a plot with u and w. Now these are three-dimensional vectors, so we got to draw them on the x, y, and z space. And if we want that angle that's between u and w, okay? And first off, what do we mean by an angle between these two? Suppose you draw a plane that contains both u and w in it, okay? Then what would be the angle of u and w in that plane? And any two vectors would span a plane. You know, any two vectors that are not parallel would span a plane. And so you would have an angle between them there. Well, why don't we use both of these expressions of u dot v? The one where you do it component wise, and the other one where you take the magnitude and the angle. So what we could do now is take this formula and divide both sides by the magnitudes u and v, and then we would end up with a expression of cosine theta being equal to u dot w over the magnitudes. And that's really nice, because we know how to do u dot w now with components, thanks to this theorem up here. So let's go ahead and start computing. The dot product between u and w is going to be, again, the first components multiplied together. That's what you're seeing here. Plus the second components multiplied together. That's what you see here. Plus the third components multiplied together. And we're going to, so that's just the dot product. And now to get cosine theta, we're going to divide by the magnitude. The magnitude of u is 2. And, we've talked about magnitudes a lot. You just take this and square it, plus this squared, and then square root. You should get a 2. And the magnitude of w is 4. Okay, you could compute that with the formula. And you get square root of 3 over 4. Now, that's what cosine theta is. If we want the angle, we take arc cos of what the cosine theta is, and we would get that it's approximately 1.12 radians, or 64.3 degrees. Now that's really nice, because if you drew two vectors like this in space, you can't eyeball the angle between them. That's not easy. You can't just sit around and say, oh, that looks like it's going to be 30 degrees over there. No, you can't do that. Now we have a very precise way of computing the angle between two vectors. So when we discussed the dot product, we said that at the end we should get a number, like up here, the number that we would get is 2 times the square root of 3. Okay, so if this is square root of 3 times 1 times square root of 3 times 1, so you'll get 2 times the square root of 3, and then this is just 0. So the dot product actually between u and w is the number 2 times the square root of 3. But what if you want to turn the shadow that one vector would leave on the other into a vector? Okay, that's where you need the orthogonal projection. It's called the orthogonal projection. So the orthogonal projection of u onto v is given by this formula that you see. So we have, what is this? What does that remind you of? V over the magnitude of v. Well, that's just a unit vector. That's a pure direction, okay? In a sense. Unit vectors give us a sort of pure direction. So we have now a vector that's in the direction of v. And what's the magnitude of that vector? It's u cosine theta. But what's u cosine theta? Okay, u cosine theta is the shadow that u would leave on v. So it's a way to take this shadow and turn it into a vector. Where does that vector point? It would point in the direction of v, okay? So that's what the projection of u onto v is. Okay, notice that u onto v, the projection of u onto v, is not the same thing as the projection of v onto u, because they point in different directions and even have different magnitudes, and so it's not a kind of a commutative thing. Why that would be useful? I mean, another example here that's found in our class. So if you have a box on an inclined slope, and the force of gravity is in the negative y direction, okay, so pointing straight down, and you just want to know the amount of force that's pulling this thing down the ramp, okay? It's due to gravity, of course, but some of that force of gravity is being redirected down the slope. That's how this thing will accelerate down the slope. So you want to know what the shadow that the force of gravity would leave in a direction that's along the slope. So we have this vector v hat, and the question is asking us to take the force of gravity, which is 0 minus mg, because you're pointing down, and project it onto this unit vector that's in the v hat direction. Well, we're going to use this formula here, which is equivalent to this. Okay. Now, why use this instead of that? Well, here we could use the formula when the vectors are given in components. Okay. So this is nice when you have all of your vectors written in components. This is nice if you're given an angle. Okay. Here we're given the vectors in components, so let's just use the formula where we use, and you could derive this from this expression. Okay. It's not too difficult. You just multiply top and bottom by v, and you would get a v squared on the bottom, which is equal to v dot v, and v, the magnitude of v times u cosine theta is the dot product, and you would just be left with v. So it's easy to prove their equivalence. But anyway, let's use that formula, and just plugging and chugging, we get this expression here. So let's find the dot product of these two. Well, this is going to give you 0 times cosine theta, which is just 0, plus negative mg times negative sine theta. Well, that's going to give you a total of mg sine theta. That's where you're getting this top thing over there. Now, the bottom is going to give you cosine theta times cosine theta. What's that? That's cosine theta squared, plus negative sine theta times negative sine theta. And what is that? That's sine squared. So what's cosine squared plus sine squared? Cosine squared plus sine squared is 1. Okay, so that's where that 1 is coming from there. And what is this guy? This is v. Okay, so you're just plugging it in there. I wrote v with a hat just because it was a unit vector. I mean, we didn't necessarily have to do that. And if you don't need a unit vector, it's just coincidental that the vector that we're using is a unit vector. But there's really no need to use a unit vector there. Okay, so simplifying then, so we'll get mg sine theta over 1 times v, and you could then, this is just a scalar at this point, right? The vector is, this is the vector, okay? What's inside the angled brackets. And you could distribute, or you could just leave it like that. I mean, I would totally accept this as an answer. But if you distribute the scalar that's outside, you would get that expression there that you see on the right. So this is the shadow. This vector here has a magnitude of the shadow that the force of gravity would leave if you shine a light this way towards the plane. The force vector would leave a shadow of length mg sine theta, and it would point along v hat. So this is what this vector is there.